So the objective of this session is to introduce the Adiabatic quantum computation algorithm, so explain what is the quantum computation, which is a particular case of the quantum annealing. So the quantum annealing are a family of algorithms that are designed to be run in analog computers. Okay, the difference between an analog computer and a digital computer is that while the digital computer, what you do is that you manipulate your quantum state by performing some unitary operations, no? So single and 2 qubit gates. In the analog computer, what you do is that you manipulate the whole Hamiltonian. So usually you initialize your system in some ground state of a certain Hamiltonian, and then you manipulate the state of this memory, of the quantum memory, by changing gradually the Hamiltonian and bring the system into a sub-Hamiltonian. So now what we will do is we present a specific case of this that will be the Adiabatic quantum computation. So the goal is to find the ground state of a Hamiltonian. Okay, in our case, an easy Hamiltonian, since this is the most particular, this is the most common Hamiltonian in the annealing platforms that we have, and as we have seen, it allows for encoding QO programs. Okay, in the previous lecture, we saw how a QO program could be encoded in the ground state of a Hamiltonian, and the idea of today, the goal of today, is to present an algorithm that reaches the best ground state of this Hamiltonian. One first option, one first strategy that one would like to try is just prepare the quantum chip that is described by this Hamiltonian and put the system down. The problem is that these couplings typically are very complicated, and the energy landscape of this same configuration has many local minima, and therefore it should be called a speedless. And then it's very difficult to find the ground state by simply pulling. Okay, so basically the idea of the Adiabatic quantum computation is different and relies on exploiting the Adiabatic theorem. So let me start from the beginning. So the idea is that we will have a mixing Hamiltonian that we call H naught. That is a Hamiltonian very easy to prepare. Is this one here. Okay, this Hamiltonian here has a ground state that is the following. Okay, the ground state of this Hamiltonian. And notice that here, this plus state is the state of sigma x, and we call the 0, 1 basis the basis of sigma z. Okay, so basically 0 and 1 are the elements of the vectors of sigma z. Okay, so the idea is that we will initialize the system in this Hamiltonian. We will pull the system down in order that the ground state, the initial state, is this state here, and the idea will be do an annealing process and changing the Hamiltonian from this Hamiltonian H0 to the Hamiltonian HP. So we will have some scaling parameter S that let's, for instance, consider a linear interpolation. This could be different, but let's consider the case that we have a linear interpolation, such that when S is equal to 0, we have the initial Hamiltonian, but gradually we will change S, and when S is equal to 1, the initial Hamiltonian has vanished, and the full Hamiltonian is just a Hamiltonian. Okay. Why I say that we are exploiting the Adiabatic theorem? The reason is the following. Maybe it helps to to draw the spectrum of this Hamiltonian HS. So I will plot the spectrum. So this is how the energy levels of this Hamiltonian HS change in time. So the ground state and changing in S. So this would be the energy of the first excited state, the potential S, and the energy of the ground state. Okay. So there will be a crucial quantity that will be the gap of the system, that will be basically the energy difference between the ground and the first excited state. And what the adiabatic theorem says is that if I change my parameter, my interpolated parameter, at a rate that is much smaller than the rate given by the gap, yeah. So if this rate is much lower than the time scale given by the gap, then the system remains in the eigenstate that it finds. In our case, as we will start in the ground state of this mixing Hamiltonian, when if we perform this interpolation respecting this condition in the whole annealing process, what we are guaranteed is that after the annealing process, we will remain in the ground state. Okay, and therefore our final state will be the ground state of the parallel Hamiltonian. But this is the objective that we had. Okay. Here, some comments are in order. Okay. One first comment is the connection of this approach with the let's say simulated annealing that we explained in the previous session. So notice that in the simulated annealing, we had a very random potential with many local minima, right? And we initially started in a random place. I will change color. We were starting in a random place, and then we were exploiting the thermal fluctuations to jump and be able to jump over these barriers and avoid getting trapped in a local. Okay. So here there's some connection with this, because notice that this initial Hamiltonian that implies this initial state, we can write this state as follows. This is simply the uniform superposition of all the So this is I have missing the normalization constant. But this is just the uniform superposition of all the possible bit splits, right? Therefore, it means that initially my wave function is spread initially. So in the simulated annealing, I was starting in some way, somewhere, in some point. Okay. Here, what happens is that my initial state is a superposition. It's exactly if you want a delocalized state. It's a superposition. So this is a diluted wave function. The wave function is spread over all the configuration space. Okay, and what we do when we just change this parameter from 0 to 1, when we do this annealing process, what we do is that we are just exploring the whole space of configuration simultaneously, and we function this shrinking until when S is equal to 1, we are we finish the annealing process and we just so the solution is just a single bit string. And notice that this Hamiltonian only contains sigma sets, and therefore it's all, so it's all the elements of its basis, all its eigenstates are product states in the computational basis 0, 0, 1. Okay? So for this reason, some people like using the analogy of the tunnel effect, in the sense that we don't jump over the barriers thanks to thermal fluctuations like we were doing in the simulated tunneling case, but somehow we are spread, we're everywhere, and basically we just tunnel below these barriers. I don't know to what extent this analogy is correct, but it's a nice way of looking at things. Okay, another important thing to mention is the runtime of the quantum computation. Okay, so here we notice that the limit that we have okay, first problem. So if we perform the annealing too fast, what will happen is that we will populate excited states of the system. Okay, and this is something that in principle we don't want to avoid. It's true that if the spectrum becomes very dense in here, maybe having excitations to the first, so having population to the first excited states of the problem Hamiltonian, what will make is that it will provide solutions that are quite good. Okay, that are not the best one, but are quite good. Okay, this is a first observation. But the idea is that if we really are dealing a very difficult problem and we want to find the solution of the ground state, we need to respect this condition. And respecting this condition will have consequences in the runtime of the algorithm. So usually what happens is that there are regions in the annealing, so in the interval of the scale parameter, there are intervals in which suspecting the condition is easy, and if you want that these lines do not shrink when you increase the system size. Okay, but usually here, from the physical point of view, what typically happens is that you have a phase transition between this Hamiltonian and this other Hamiltonian. These are Hamiltonians of very different nature, and usually what happens is that you have a region for a point in the spectrum that we call S star, okay, in which the gap tends to close when you increase the system size. Let me be a bit specific with that. Good. So another important feature to mention is the runtime of the algorithm. Okay. So here we notice that the gap of the system at the position S star, right, when S takes the value S star, shrinks. And it can shrink in several ways, right? So the gap of the system at star, it can shrink in several ways. And here, okay, let me mention the following. So we know that when things shrinks, I mean that when you solve the same problem for different system sizes and for increasing system sizes, what happens to the gap? Typically, what you see is that you can have an exponentially closing gap. That means that this scales shrinks exponentially the system size, where n is the number of qubits that you have in your problem. Okay, or sometimes if you are lucky and your problem is not so difficult, what will happen is that you will get a polynomial during the gap. Okay, basically, this scaling here is what defines the runtime of your algorithm. If the gap shrinks exponentially, your runtime will scale exponentially, and then you will only be able to solve the problem for small instances. So problems that are not very big in size. Here, in practice, if we want to run an adiabatic quantum computation in a quantum computer, one crucial quantity is the coherence time of the qubits. Okay, not all the platforms offer the same coherence times. I know that the wave that has many qubits available offers coherence times of the order of 40 nanoseconds, and other companies like Kilimanjaro, for instance, offer longer coherence times because they work with high coherent flux qubits, and they have coherence times of 1 microsecond or 2 microseconds, although they have many less qubits available. Okay, so here there is, depending on the problem, you will have to choose one solution or another. Okay. What else? Yes. So basically, this will be the main limitation of your algorithm. Basically, it tells you how difficult is the problem that you can tackle. In this aspect, one could consider alternatives. So the fact that for a particular path, for this complete interpolation that you want to go from this Hamiltonian to this other Hamiltonian, you are finding a transition that's really in some scaling. It doesn't mean that maybe you can find an alternative path that can provide better results. So that can provide let's say run times that are better. Okay, so there is a whole world of, if you want, optimizing a Hamiltonian path. So finding what's the best route to target your problem Hamiltonian. Okay. One last thing that I would like to comment is that how you read the result of your computation. No? So the idea is that first we initialize the system in the ground state of this initial Hamiltonian. Then the system becomes an equal superposition of all the configuration states. Then we perform the annealing process, changing S from 0 to 1 till we reach the ground state of the Hamiltonian, of the program Hamiltonian. And the last thing that we will do to read out the result is performing a measurement. Okay. Here, unlike other algorithms, because the Hamiltonian, the target Hamiltonian is diagonal on the conditional basis, okay, and the ground state will be a product on the conditional basis. The only one thing that we have to do is just create test cases, and then we will just the measurement obtained. So a single measurement will be enough, okay, to see what's the solution of your problem. This is of course in the ideal case. In practice, you do several runs and several iterations because there are always errors happening, and then you have the chance of either that some measurements, the measurement process is not perfect, or there are always some imperfections, and also that you sometimes you can get you didn't go sufficiently slow and you excite or you have population in the first states. But in the ideal case, a single measurement would be enough. Okay, so these are the main things we wanted to explain today of the adiabatic computation. This is an example of algorithm that needs to be run in an analog machine in which you can control the Hamiltonian. We have seen that it's simply performing an interpolation from some initial Hamiltonian that brings the system into a superposition of all the configuration space of your possible solutions. And by means of this annealing process, we reach the ground state of an easing Hamiltonian that basically encodes the solution of the Kubo problem we wanted to solve. The main limitation is how the gap shrinks, that this typically decreases with the system size, and depending on the scale of this shrinking of the gap, the runtime of the algorithm is longer or faster.